Okay, so today we'll finish chapter 3. So the remaining parts of the chapter 3 are just some special cases that I want to talk about. So there are actually no new theorems or no new calculation tools that we will actually learn, but there are some interesting special case that I want to mention. Okay. So last time you may still remember that we talked about a slightly different cases for the Green's theorem, right? So usually when we talk about Green's theorem, so we have a closed curve C, and then the region A, right? The area enclosed by the curve, right? And then the area A, usually we consider the completely filled area, right? So, but last time we considered a special case where the area, we basically make a hole out of the area so that the region that we are considering actually has a hole, right? So, and this time we are going to consider the divergence theorem. So this time, again, we are considering the region with a hole. Okay, so let's see the setup. Okay, so usually, right? So usually when we have when we use the divergence theorem, right? So first of all, we have this closed curve. So for example, here a spherical surface, and we are considering, right? So the volume, the entire completely filled volume inside this of this closed surface, right? So the divergence theorems that we have learned is that the outward flux, right, of this vector field, right, through this closed surface, right, so would be equals to the volume integral, right, so of the divergence density, right, the flux density, right, so over the entire volume, right, so enclosed by the surface, right. So again, so physically, what does it say? So go back to think of the case of the airflow, right? So imagine that our vector field, right, describing the air velocity, right? So of different points in space, right? So and then the outward flux, what does that mean? So that means the amount of air that escape this region, right? So per unit time. So that's the physical meaning of this outward flux, right? So and that equals to this volume integral of this flux density, right? So that's the physical picture was clear, right? So now I'm considering the picture below. So I have again a big closed surface, this big sphere, but you can see that inside I have another smaller sphere, which is another closed surface. Okay, so of course these two does not have to be spherical. Okay, so that it's just a big closed surface and then a smaller closed surface. Right. So now the region enclosed by the smaller closed surface is a cavity, right? So or a hole, right? So basically, the volume that we will be considering is this part, right? So it's between the outer surface and the inner surface. So now I'm going to ask the same question: is that again, air flows everywhere. So I'm not drawing the vector field, but imagine the vector field is there, right? So I'm considering, I want to ask is how much air is escaping this region, right? So per unit time. Okay, so this region again, remember, is the region between the two closed surfaces. Okay, I want to ask how much air is escaping, getting out of this region per unit time. Okay. So when we are talking about the air escaping, right? So in the case above, right? So the only way that the air can escape from this region is to get out, right? So like this. However, in this case, you could imagine that the air can get out, right? So to the outer space essentially, right? So or the air, if it escapes into the hole, right? So that is also considered to be escaping, right? So as long as it's get out from this region. So that in this case, so that means there are two paths or two methods for the air to get out of the region. Right? One is getting into the outer space, and the other is getting inside the cavity, the hole. Right? So, and in this case, then the flux that we consider will be consist of two terms now. Right? So again, the first term here is the flux through the outer surface, right? So the air that gets into the outer space. And then now we have a second term here, right? So this is also a flux integral. And remember, N2, so pay attention to N2. So N2 is a normal vector pointing this direction to this direction. Is actually a vector that's kind of pointing inside, right? So into the origin. So, but although it's pointing inside, but in the sense it's also pointing outside, right? Because it's pointing out of the origin, the region that we care about, right? So then the first term, right? So represent the air get out to the outer space, and then the second term represent the air get into this cavity. Right? So then that would be the total loss of the air, right, per unit time. So and this combining these two terms would be the volume integral of the flux density. Okay. So I hope physically it is reasonable that we need the second term. Okay. So now that's the physical picture. I hope it is clear, but let's just also work out the math. So just to do a simple proof on in this case where we have this region with a cavity, the divergence theorem is modified in this form. Okay, so let's do a quick proof. Okay. So again, let me consider the two surfaces individually. Okay. So the big one here, right? So I call this S1, and then I call this the entire solid region. Okay, I call this V, the entire region inside. And then I define this to be the normal vector N1. So it's just the same as how I defined it in the last slide. Okay. So now I draw the second smaller surface, okay, individually, okay, just here. So and then the normal vector. So eventually you understand that we are going to consider the normal vector pointing into the origin. But first, let me define a normal vector also pointing out. Okay, this I call this n hat prime. And then this smaller surface, I call this S2. Okay. So, and the region inside this smaller surface, which is the region of the cavity, right? So I call this, let me call this V prime. Okay. So now, if you just consider the first case, right, individually, again, without any cavity, right? So then we just apply the form of the divergence theorem that we have already learned previously, right? So it's just this one. So this is just the same divergence theorem that we have learned before, right? So no question here. So now, if I consider, right, so this smaller surface, right? So and then I also apply the divergence theorem. just treating this one itself as a whole system, right? So then the divergence theorem can be again written like this. Right? So these are just the same divergence theorem. Okay. So now let me define the unit vector that we actually care about. So here I'm actually care about the normal vector that is pointing into the origin. Okay, so this N2. So here, let me draw N2. So N2 is actually this one. Right. So the N2 vector that we will care about is actually pointing in the exact opposite direction of this N hat prime that I draw here. So then let me write here is the N2 hat is equal to minus N hat N prime, right? So that's the relation between these two normal vectors. So then let me talk, if I look at the left-hand side of this equation, right? So if I look at the left-hand side of this equation, so this N hat prime is actually minus N2, right? So then the left-hand side is actually can be written as okay. So this N hat prime is equals to minus N2 hat, right? So that's why this one is equals to this black term here. So on the right-hand side, nothing is changed. Nothing is changed for the right-hand side. Okay. So here now I got one equation, right? So in blue, which I call 1. And then on the right-hand side, I got this black equation, which I call 2. So now, if I do 1, subtract the 2 equations. So equation 1 minus equation 2. If I do equation 1 minus equation 2, then the left-hand side is this. So minus the negative of this term. So minus 2 minus signs, or then I actually have positive. Okay. So that's the left-hand side. So and the right-hand side would be this volume integral minus this volume integral. Right. So the volume integral over the entire region minus the volume integral over this region, right? So the size of this region is exactly equal to the size of the cavity, right? So then that means, right? So now you need to basically put this so just imagine that you put this sphere, right? So back in here. So again, I call this region only as V1, right? So as I stated in the last slide. So that actually the right-hand side is equals to the volume integral, but for V1 only, right? For this region only. And that finished the proof, right, for this version of divergence theorems when we have a region with a cavity. Right? And again, right, you could imagine how you can generalize the same argument, right, for a region with, even multiple holes or multiple cavities. So with that, I actually want to apply it, right? So for Gauss's law, okay. So I'm sure that you have already learned Gauss's law in 2041, right? So and what Gauss's law tells you, right, is that, well, I'm just considering Gauss's law for 1-point charge. Okay. So if I have 1-point charge, right? So if I construct a closed surface, so around this point charge, then Gauss's law tells you that the flux of electric field, right, so is equals to the amount of charge enclosed divided by epsilon naught, right? And the important point is that it doesn't matter how you draw the closed surface, right? So the closed surface can be a sphere, a spherical surface, or a surface of this irregular shape, right? So, but as long as your closed surface is enclosing your charge, then the flux of electric field is still given by Q divided by epsilon naught, right? So this is something you have learned. And I'm sure that you also have learned the proof, right? So on why the flux is independent of the shape of the surface that you choose. Okay. So here I just want to give you kind of a second proof, right? So based on the divergence theorem that I've just talked about. Okay. So just give you a second perspective. Okay. So what I'm trying to prove, I'm trying to prove that the flux, right, so is independent of the flux of electric field is independent of the shape of the surface that you choose. Right? So that's what we are going to prove. So what I'm doing here is that I'm going to overlay both of these surface, right, so onto the same picture, right? So you can see that I have this blue spherical surface, which is the case on the left, and then I have the arbitrary surface, the red one, which is the case on the right. So then I put these two surfaces together, right, on the same picture. So now you can see that I am forming a region that has a big hole, right? So in this part, right? So the S2 is the big one, the biggest one with this arbitrary shape, and this S1, I suppose, is a slightly smaller one, but with a spherical shape, right? So if you look at this case, right? So and compare with this case here, right? So they're talking about the same thing. It's just that now here I'm not talking about two spherical surfaces anymore, right? So the outer one is a surface that has an arbitrary shape. Okay, so now I want to apply divergence theorem. So for this region without cavity, right? So the region marked in green. So I'm going to apply the divergence theorem. So what does divergence theorem give? Right. So the volume integral for the divergence of E, right? So over this green region only, right? So will be equals to the flux, right, of electric field through the red surface plus the flux of the electric field through the blue surface. Okay. So, but here again, pay attention to the direction of the unit vectors. Okay, so when I do the flux through the outer surface S2, notice that N2 is pointing out. Okay. So, and when I consider the flux through this blue spherical surface, so I define this one, right? So this vector is actually pointing into the origin as minus N1. So then this first term, okay, so I'm considering the flux, right? So towards the origin. And the second one, the flux outward. Okay, so that's really just applying this exact same divergence theorem that I just talked about. Okay, nothing, no additional trick, direct applied the theorem. So now I want to, what do I want to prove? So I actually want to prove that the two flux, okay, so the flux through the blue, right, so pointing outward, and then the flux through the red also pointing outward to be equal. So to do that, basically I need the right hand side to be 0. The right hand side. So now we need some knowledge about the properties of the electric field, which is the Coulomb's law. Okay, so you know Coulomb's law, then you know that what is the divergence of E. Right, so using the formula that I mentioned last time, right? So that you have the E. Right, so let me remind you what is E. So E is in spherical coordinates, right? So E is this one. Coulomb's law, spherical coordinates. Apply the formula for divergence, you will find that the divergence of E is actually 0. Okay, for R to be at any points that is not at the origin. Okay, because you can see this 1 over R squared. Okay, so but we are safe. We are safe. We can say that we are only considering the point that is not in the origin, because we are only considering any point in this green region, right? So any point in this green region, of course, is not at the origin, right? So I can say that in any point in this green region, the divergence of E is 0. Okay, so we are this volume integral. Well, that's the nice thing, that this volume integral is not including the origin. Right. So that's why we are safe. We can simply say that the divergence of E is 0. So then the right hand side is 0. So then that means this term plus this term is 0. So and at the end, so that means this flux, right? So for this S1 is equals to the flux, right? So through this S2. But okay, one thing again, pay attention is that the final result, this flux is talking about the flux outward, and this flux is also pointing the flux outward. Okay, so by outward here I means that the direction that is away from the origin. Right. So remember, the one that is pointing into the origin is minus N1. Okay, so but here the final result, okay, is the flux, okay, dot N1. So N1 is actually pointing this way. So this show that the flux, right, so is indeed independent, right? So of the shape that you choose. Okay. So and I'm sure that in 2041 you also have a proof, but without using divergence theorem, I believe that you consider the solid angle, right? The solid angle. Okay. So just now I use an important result is that the divergence of E is 0. So, but here maybe you find something that is strange. That is that when we talk about the divergence, right? So we imagine that this is a tool for us to characterize whether the field, the vector field, is diverging, right? So or not, right? So that's the purpose of having this so-called divergence. So then if we think of the electric field, right? So this is the electric field from this point charge. So from by your eye, so you look, you can see that okay, it must be so all the vectors are pointing away from the origin. So it looks like things are diverging out, right? So, but now I suddenly tell you that no, actually the divergence of E is 0. So at least for the points away from the origin. So it seems that this violate our intuition here a little bit, right? So then here I would like to clarify this, okay, by considering these three cases. So if I just give you these three fields, so you can see that in all cases, right? So the vectors are diverging out, right, from the origin, and intuitively, I would say that okay, they are all having some non-zero divergence, right? So, and what are the difference between these three cases? You can see that in this case, I have this f equals r squared r hat, and in this case, this f equals 1 over r squared r hat, and in this case, is f equals 1 divided by r cubed r hat. Okay, so in all three cases, right, so the vectors are pointing out of the away from the origin. The difference is that in this case, because of the r squared, so that means that when you get further and further away from the origin, the vector is actually getting longer and longer. Right. So and in this case, is the other way, right? So because of this 1 over r squared dependence, when you get as you get further and further away from the origin, right? So the vector field is getting the vectors, the magnitude of the vector is getting smaller and smaller. Right. So this one even the decay is even more rapidly because of this 1 over r cubed. So, but regardless, if we look at all these three cases, right? So and then I want to calculate, okay, so the divergence of the vector field. Okay, so then it's not difficult, right? So just apply the formula that in the lecture notes, right? So the divergence, right? So in spherical coordinates. So in general, let's say I have this f equals 1 divided by r to the n r hat. Okay, n is any, well, let's say any any real number really. It can be positive, it can be negative, right? So we can see that if I put n equals to -2 is actually this case. If I put n equals 2 is this case. If I put n equals 3 is this case, right? So this general formula includes all three cases, or even many more possible cases. But let's say I have, in general, I have this form. Okay, the field looks like this. Then if I take the divergence, okay, in spherical coordinates, so this would be easy, right? Because again, so all this field does not have theta and phi components, and it does not depend on theta and phi. So then taking the divergence in spherical coordinates is very easy. But anyway, what you would get is this one, right? This one. So again, let's avoid the origin point, right? So we know that something's wrong at the origin point because the function blows up, right? So in this case, but so at least, right? So for any points that is not at the origin, right? So the divergence of f given by this 2 minus n divided by r to the n plus 1. Okay, so now you can see that, okay, of course, most of the cases it can be is non-zero. You can see that, except for one case. That is, if you have 2 minus n equals 0, then actually the divergence of f is 0 everywhere. Okay. And actually, the n equals 2 case is exactly the case for your Coulomb's law. Right? So if you have set n equals 2, then this is 1 over r squared. That's the Coulomb's law case. Right? So, and well, that's just a verify that yes, the divergence of E is 0. So then now the question is how do we make sense of it? Okay, so by our eye, it seems that all the fields are diverging, right? So away from all the vectors are pointing out from the origin, right? So, but in this case, specifically in this case, the divergence of the field is 0. So how do we make sense of it? So that goes back to the original definition of divergence. Okay. So how was this divergence defined? So remember when we tried to derive the formula for the divergence, we were considering a very, very small region, right, of space, right, and consider the flux through a very, very small box. Right, so you remember that if let me draw, like, let's say a very, very small box here, right? So the divergence of a field is telling us that, okay, so at this region, right, so whether we have flux through this small box. So that is the divergence. So that the divergence, when we talk about divergence, we should really think of a local behavior of the field, a local behavior of the field. So in fact, let's say if I consider, okay, so let me again borrow this picture. Okay, so let me borrow this picture here. So let me borrow this picture. This is the 1 over r squared field. Okay. And now, as I said, if we want to consider the divergence of the field, right? So we need to first, right? So basically, we need to draw a box, right? But okay, this box should be much smaller, but I need to draw it big enough to include a few of the arrows. So just imagine that this is a box. Okay, so it actually can be big. Okay, the argument still works. So if I say that the divergence of the field, so in this region, is 0. So then what would I have is that the outward flux, the flux that's going out of this region will be equal to the flux going into this region. Right? So then that would give the divergence to be 0. And indeed, okay, so it is the case. So although, right, so the field all pointing away looks like diverging, but if we want to consider the flux, right? So what we, okay, let me actually try to draw a box instead of the square. So we really need to consider the flux through all 6 faces of this box. Right? And you can see that, of course, the bottom face, in this case, the bottom face is basically the only face that will receive an inward flux. Right? So the bottom face will have this field going in. Right? So, and you can see that because the bottom face is closest to the origin, then the magnitude of the flux, of course, would be the greatest, right, for the bottom face. So then the bottom face received a lot of flux, and then you see that, okay, what about the top face? Well, the top face is further away from the charge, so then the field in this position will be weaker, right? So, but the area that I have is the same. So that means that actually the phase, the flux, the outward flux, right? So that passing through the upper surface would be actually smaller than the inward flux passing through the bottom surface. So that you can see that if you just consider the upper and the lower phases, then you see some an imbalance of flux. However, that is not the end of the story. You still need to consider all the 4 phases on the 4 sides. And in fact, for example, if you consider the phase on the left, and you can see the vector field is pointing this way, right? And then if you consider the phase on the right, the vector field is pointing this way. So that means, in fact, for all the 4 phases on the side, you have some outward flux also. So that means for the bottom phase, you have inward flux. For the phase on top and all the phases on the side, the 5, you all get outward flux. Right. So that's 5-to-1, but of course it really depends on how strong the flux is, right? So on in the individual phase, you really need to do the calculation, right? So to see whether they eventually cancel out or not. Right? But at least you could imagine that in the special case, right? So it is possible that the inward flux, right, through the bottom surface just so happens to balance out, okay, the outward flux of all 5 phases. Okay. And that would be the case when we have this, if you have the flux to be equal to 1/r squared. Okay. But of course, there's even a slightly easier way to think about it, because, well, clearly we are using spherical coordinate. Right? So when we consider the shape of the box, right, so the most convenient choice won't be this regular cubic box, right? So what you really want to, it's easier for you to think about is actually consider a box like this, right? So in this case, you actually would you understand that the flux only passes through this and this phases. Right, so if you construct your box like this, you understand that you don't even need to worry about the flux through the four sides, right? Because in this case only as the R component, the flux through the four sizes will be zero anyway. So then that means in this case, all you need to have is that you can see that up here I have a bigger surface, and down here is a slightly smaller surface. So then if your field here is slightly weaker than the field here, right, such that, right, the decrease of the field is compensated by the increase of this area, then you will see that the net flux right through this small box will be zero, and then you get the divergence to be zero. Okay. So then the take-home message is that it's just that we need to be careful about associating, right, with the appearance of the field, right, with the divergence of this, right? So they all look divergent field, okay, but when we talk about the divergence of field, we are really talking about the local behavior of the field. Okay? So you really need to do the calculation before you can tell. And it turns out that, but this special case is very important, right, for you, because Coulomb's law, right? So because of Coulomb's law, you basically deal with this, right? So a lot. So you actually rarely deal with 1 over R cubed, right? So that's why. So this is an important remark. Okay. Okay. So now a few more words about this divergence, and this would be, I would say, completely beyond the scope of this course, but you will see it again in 3041. Okay. See it again in 3041. Is that if we go back, 3041 is E and M, right? So you'll go back to consider that. But let me just give you kind of a warning or just a preview. Is that now if I go back to look at this Gauss law, right? So this one, let me just consider this one. So and then I apply the divergence theorem. And this time I want to apply the divergence theorem on the entire region. Okay, I'm not constructing a region that is with a hole anymore. I want to apply the divergence theorem so on to this entire region, and enclosed by this S1. So that then what would that tell us? So then right, the flux would be equals to, right, so this volume integral of the divergence of E. So but just now we learned that the divergence of E is 0 everywhere, except at the origin that I avoided to talk about it. Right. So because we know that the field like blow up to infinity, so that's why I avoided to talk about the divergence at the 0 point. But if we actually just try to apply the divergence theorem for the entire region, then we'll have this triple integral. And this triple integral, right, so still has to be equals to this Q divided by epsilon naught, right? So then what does that mean? So when we integrate this volume integral, so everywhere is 0, but except at the origin that we don't know how to deal with. And it turns out that the physicist, right, so has invented this function, so-called the Dirac delta function. Okay. Dirac delta function. I'll just giving you a name. I'm not actually going to teach it, but as a preview, so as I said, you'll see it again in 3041, is that the divergence. What is a Dirac delta function? Dirac delta function is that it is 0 everywhere, except at the origin. So at the origin, the function value is infinity. infinity. So, but so you have one point with an infinite value and then all 0, but the requirement is that you integrate this function, you still give you a constant. And the introduction of this Dirac delta function, okay, fix this issue here. Okay, so here, just a preview. Okay, so all right. So and then let me also finish the last 1 or 2 slides so before having a break. So then I just reminded you that, okay, so I just clarified that, okay, even the field looks like it's diverging, but in this specific case, it may not be. So what about circulation? So, and we remember that, right, so the diverging field, and then this is a circulating field, right? So the looks like a vortex. So, well, and also we associated this kind of field with what? With the curl, circulation density of the field, right? So the curl of F. And again, here is what I want to tell you is that, yes, in these 3 cases, let me introduce these 3 cases first. So you can see that, okay, they are expressed in cylindrical coordinates. You can see that in this case is F equals rho square phi hat, right? So phi hat is the unit vector. Remember, phi hat is a unit vector that is always pointing tangential to a circle, right? So that is the circle center at the origin. So then this field only has this phi hat. So that means that all the vectors, so going along, so it's tangential to a circle. And in this case, because I have this rho square vector in front, so that means the magnitude of this vector is getting bigger and bigger as you go further away from the origin, right? So, and in this case, right, so I have this 1 over rho, so that means that if you are near to the origin, then you have a very large magnitude vector, but as you go further away, then the magnitude getting smaller and smaller, right? So 1 over rho square will decay even more rapidly. So again, just by our impression, looks like all the fields are the so-called circulating. Right? So, but now try to take the curl. We take the curl of this field. Okay. So again, I'm going to make this general form F equals 1 divided by rho to the power n. So again, n is any positive or negative real number. So then n equals minus 2 is this case, right? So again, n equals 1 is this case, n equals 2 is this case. You can have n equal 4, n equal 5, and so on. But regardless, if you just have this simple general form, you take the curl in cylindrical coordinates. Then again, you get this general formula here. Okay, so 1 minus n divided by rho to the n plus 1. So this time, again, you see that most of the cases, you get some non-zero number, except when n equals 1. Okay, when n equals 1, that is this case here. Okay. So the curl of F in this case is actually 0. Again, how do we make sense of it? Is that, remember, the divergence and also the curl, so are examining the behavior, the local behavior, right? So of this field is examining a very small region, right? So then that means we need to consider, right? So really the line integral, so around a small region, right? So in this field, so let's say I'm going to consider a small loop, right? So we need to well, again, what does the curl of f tells us is that the f dot dr, right? So around a very small closed loop, right? So then here, let me make a convenient choice of the shape of the loop, which is like this. This green, the solid green one. So these two arcs, that is the arc of the circle. Okay, so again, just imagine that this is very small. Okay, so I need to draw it big, but imagine that it's small. Or even you can consider it as a regular size. That's actually okay. I'm just going to consider basically I'm just going to consider the f dot dr, right? So over this loop here. So because of the fact that the field, right? So the field always go along, right? So the field always go along these two lines, and actually the right. So and that's why when we talk about the line integral, so over this loop, I only need to worry about this part and this part. But I know that the f dot dr for this line is 0, right? Because the f is perpendicular to this line, and the f dot dr, right? So around along this line also 0. So now I'm going to draw do the line integral, right? So to do the line integral again, so by convention, I pick the counterclockwise direction as the line integral. So I have just two terms to take care of, right? So this term here. So the f dot dr is actually just equals to the magnitude of the force times the length of this arc. But I don't actually need to do the integral because of the fact that the force, the field does not depend on the angular position, right? And that's why I will just write this. So let's say, okay, let me also say that, let's say this is row 1, okay, and then the bigger radius, this is row 2. So the line integral, right, for this smaller arc is the magnitude of the force along this line times the length of this arc. Okay. So the length of this arc, would be, what is it? The length of this arc would be this radius, rho 1, times this angle here, So let me call this delta theta. So this length, rho 1 delta theta. And actually, I need to draw add a minus sign, okay, because I'm going along this way, but then the field is pointing to the opposite way, so minus. So similarly, if I consider the integrate f dot dr for this bigger arc, then it would be this. So now, if you want the curl to be 0, so that means I need to have the f dot dr around the closed loop to be 0. And that means is this term, that means is this term plus this term to be 0. Okay. And that require and that's exactly the requirement of the 1/ρ dependent, right? So if your field satisfies, right, so this, then actually even your field looks like is circulating, but actually the curl is 0. So in this one is exactly the 1/ρ dependent field. So again, why do I want to spend some time on this special case? Because again, this is the case that you see a lot when you talk about the magnetic field from a current wire, right? A straight current wire. What is the magnetic field, right? So if you have a straight, infinitely long current carrying wire, right? So remember that your B field is, right? So it's some factor mu naught I over the 2 pi or something like that. Right? So this 1/ρ dependence, right? The vector field with this 1/ρ dependence, actually the case that we see a lot. Okay, so at this point, I will end this chapter. Actually, let me mention one more thing. In this, I made a typo in one of the previous lecture set, lecture note set. Is remember on this brief notes on this different coordinate system. Okay, so let me change it here. Here, it will be d theta dt, not dr dt. Okay, was typo here. Okay, so that's the end of chapter 3. So let's take a break for 10 minutes, and then we'll come back for chapter 4. Okay, so and for midterm, okay, for midterm is from chapter 1 to 3. Okay, so up to here. So, and in fact, I would say chapter 3 is the most, at least to me, that's my personally, I think chapter 3 is the most difficult. And chapter 4 would be ordinary differential equation. And I believe when you took your math class last year, okay, you might have learned it once already. So chapter 4 is ordinary differential equation, okay, which I'll talk about in 10 minutes. And then chapter 5 will be matrix. And chapter 6 is infinite series. Okay, so let's take a break. We'll start again at 12:40. Okay, so here comes to chapter 4, which is ODE, right? So ordinary differential equations. So I'm sure that you have seen ODE before, and not just in math class, but probably in mechanics class, right? So when you solve the equation of motion, so from the Newton's law, right? So if the force themselves are not constant, right? So changing a function, right? But instead, if they are changing functions of position or even changing functions of time, right? So then your Newton's law will give you the equation of motion that in the form of ODE. So then in this chapter, we are going to talk about techniques in solving ODEs of different kinds. Okay, so we will talk about the first order ODE and then the second order ODE. Okay, so then let me first give the most general definition of ODE, but of course, at the end of the day, we are just going to consider these specific types of ODE. Okay. So by definition, okay, so an ODE, an ordinary differential equations, okay, is an equation that contains, okay, ordinary derivatives. So ordinary means that it's not partial derivatives. So ordinary derivatives, that means right, so we are considering the function of one variable and take that derivative. So ordinary derivative, not partial derivative. So this ODE will contains, right, so an equation that can be expressed as a function of some derivatives, right, and also so let's say the function we are considering is y as a function of x, right? So then the ODE can be written in this form. So this is a function of the derivatives of y and also y itself and maybe also x. Okay. So this f, right? So it can be in general it can be a very complicated expression, but regardless, it's just an expression that depends on x, y, dy dx, right, and then d square y dx square, right? So and the higher order derivatives. So of course, examples will be given later, but in this case, okay, in this case, you can see that I'm considering this function that depends up to the nth order derivatives, let's say. Then this ODE will be called an nth order ODE. Okay, so the order is determined by the highest derivative that appears in this equation. So that means, so what this f is really can be very, very complicated, right? So let me just make something up. So let's say f, right? So x, y, dy dx, d square y dx square. Let's say this is equals to sine of x plus y square plus dy dx times y plus x times d square y dx square. So you can see that this so-called function, this big f, can be a function that is very complicated. So anything that you can think of, and this expression, right, will depends on x, y, dy, dx, and so on. Right. So and this all equals to 0, or equals to some other function, or equals to a constant. Right. So that's what happened in general. So but one of the types of ODE that we'll consider a lot is a much more simple type, which is known as the linear ODE. Okay, so linear ODE is not the only one that we are considering, but this is a very common type. Is that for linear ODE, right? So the left hand side, Okay, so the left-hand side can be simply expressed in the form of a linear polynomial, okay, in y and its derivative. Okay, so y appears here, dy dx appears here, and then the higher order derivatives also appears here. Okay, and these are linear polynomials in all these y and derivatives. So because they just appear as a linear term here. So then what is nonlinear? Then you could imagine that if here I have a y square instead of y, then that would be nonlinear. If this is not dy dx, but dy dx to the power n, right? So then that would make this polynomial nonlinear, right? So similarly, if this is the nth derivative, right, to the power m, right? So or if this is the sign of this derivative, then again it won't be a linear polynomial. So then whenever you see this form, right? So then we call this a linear ODE. And now you can see that for each derivative terms in front, we have some coefficient function. So these functions are any function of x, but x can be this function of x can be any function. Okay, so they don't need to be linear. Okay, this one can be, for example, x squared, right? This one can be sine x. This one can be log of x, right? So this one can be cosine x. So if all these coefficient functions, they can be any function. So okay, these coefficient functions themselves don't have to be linear functions, but still you call this ODE as a linear ODE. It sounds complicated, but let's just let me just give you an example. Okay, so if I have the first order ODE, right? So if it is a linear ODE, then it will take this form, right? Why is this first order? Because the highest order of derivative that appears is the first order derivative, dy dx, right? And this dy dx here is not a dy dx square, right? So, and this is not y square, this is not sine y. So these two are just linear term. So then this one is known as the linear ODE. So now if I want to have a second order ODE, but still linear, right? So all I'm doing here is that add and this additional term, right? So with the second order derivative, but still individually, this is a linear term, this is a linear term, this is a linear term. So then what about right, nonlinear example? So then in this case, if I consider the first order ODE but nonlinear, then these are some examples. Okay, so as I said, if this is not dy dx but dy dx square, right, this will make the whole thing nonlinear. And also in this here, you can see that if this dy dx term in front, I don't have a function of x, but instead of a y here, then this will also make the ODE nonlinear. And also the third example here, right? So instead of having just the y here, but then I have a sine of y, and this also make the equation nonlinear. So then for second order ODE, right? So here, right? So if I have this dy dx square, so then this, and also this y is not just y, but y to the power 3, then nonlinear. And then this one, right? So the coefficient function, not a function of x, but it's a function of y, is also nonlinear. So then in this first part of the chapter, so first of all, we are going to consider first order ODE. Okay, so that means the highest order derivative that we'll see is simply dy dx. Okay. So if we just consider linear ODE, right? So it's in this form, and there's a standard method that we'll learn, which is known as the integrating factor, which of course I will talk about. And then now, in addition to this one, I will also consider several other types of first order ODE. Okay, and some of these types, some of them can be nonlinear. Okay, but it would be looks like one of these four forms. Okay. So for example, if I have this dy dx equals f of x, that's one type. And so the methods are all listed here. I will go through them one by one, right? So, and of course, for each type, I'll try to, at least for some of the types, I'll try to give some examples in physics. And then this type, so dy dx equals f of x times h of y. Okay, so all these two, right? So can be nonlinear, right? So it depends on what is your f function, right? So if this f function is x squared, or if it is sine x, then this one is already nonlinear, right? So and also here, right? If your h of y is not just y but y cubed, y squared, then this whole thing is nonlinear. So and in this one, so we will have this method of separation of variables, which I will talk about. And then the third type, okay, so is that dy dx equals to a function, also a function, but this function can be, let's say, it can be expressed as the function of the ratio of the two variables. Again, I'll explain. Okay, this will be known as the homogeneous equation. So but unfortunately, okay, so later you also will learn another type of ODE, which is also called homogeneous equation. But don't be confused. Okay, so homogeneous, the name homogeneous has been used twice. Okay, for two different type of equations. But I'll clarify again when we get there. Okay, and then this fourth type, that known as the exact differential form. Now, okay, so these are the 5 types that we'll learn. So all of these types have their own standard method. Okay, that we'll learn. Okay. And so they are not difficult. Okay, so just the method is very easy to follow actually. Now, if we have some ODEs, okay, that are neither any of these types, okay, so then the strategy that we will do, then I will say that there is not a general method, but the strategy that we will take is that we'll try to do some change of variables. Okay, so to make the ODE that we are dealing with looks like one of these. Okay, and then we can apply the standard method. So then let's go through them one by one, right? So I will go from the easiest type of ODE first, is this type. So if I have an ODE of the form, right? So dy dx equals f of x, right? So f of x can be well, for example, f of x can be x squared plus sine x, right? So that's one example, right? So the x cubed plus log of x, right? It could be e to the power x, right? So many choices, right? So if whenever you have this ODE that looks like dy dx equals f of x, so what would you do? So basically just integrating both sides, right? So integrating both sides, you're integrating the left hand side, right? So you are undoing the derivative, right? So the y, and then the right hand side, right? Just the integrating this f of x dx. Right? So that's the most kind of the trivial type of ODE, right? So this is a type that even secondary school student can do, right? So the only question is whether you can find this integral, right? So now the next So then that's the first type already. So the first type done. So the next one is that I have this ODE of the form. Okay. dy dx equals to a product of two functions. A function which depends on x only times another function which depends on y only. Okay. Then the method that we'll use here is known as the separation of variable. Okay. So what we do here is that we are going to first, right? So you can see that I move this h of y to the left hand side. So then this is what we have. And then next, so basically, notation wise, so we basically treat this as a fraction here. So then I basically put dx to the left, to the right hand side. Okay, put this dx to the right hand side. Then this is what I got. 1 over h of y dy equals f of x dx. So then now, here you can see that the left hand side only depends on y, and then the right hand side only depends on x, and then we integrate both sides. Okay, we integrate both sides. So this method, right? So it's known as the separation of variables. So here, so why don't we just integrate both sides in the very beginning? So can we just do this? Right. So you realize that if you just try to integrate both sides directly, right? So the left hand side is y, but then the right hand side, you realize that you don't really know how to do, right? Because you have this integral of f of x times h of y. So until you know the relation between y and x, right? So then you are not able to do this integral, right? Because you need to express everything in the integrand in terms of x, right? Before you can actually do this integral. But right, so but the purpose of solving this differential equation is to actually find out y as a function of x. Right, so but since you don't know y as a function of x yet, then right, so doing this integral is just not possible. So then this method of separation of variable, right, so help us to deal with this kind of ODE. Okay. So then of course, let's try one example here. So let's say I have a differential equation looks like this: dy dx equals to 1 over x times 1 over y. Okay, so on the right hand side, you can see that this is a function of x. This is a function of y, right? So as I said, the strategy is that you put everything related to y on one side of the equation, and then put everything related to x on the other side of the equation. Right, so in this case, I'll just put the 1 over y to the left hand side. Then I will have y dy. And then put everything related to x to the right hand side. So then I will have 1 over x dx. So now I'm ready to integrate both sides. Right, so integrate y dy equals integrate 1 divided by x dx. So left hand side, what is it? It would be y squared divided by 2, right? But it's an indefinite integral. Of course, let's add a c, a constant. So what about the right hand side? What is integrate 1 over x? What is integrate 1 over x? Don't know what is the function after you integrate 1 over x? Have you learned that natural log? You have learned about natural log, right? So, but here is the one remark. Okay. So you have learned that d dx log of x is equals to 1 over x. This is what you have learned. But when I write down this, so basically we are considering x greater than 0, right? Because log function is only defined, right? So log function is not defined if x is negative, right? So however, when I do this integrate 1 over x dx, right? So I did not know the range of x, right? So the x could be negative, right? The x could be negative. Then if I integrate this 1 over x, right? If x is positive, of course I can just say this is log of x. But if 1 over x is negative, then what should we do? So then here we need to consider two cases. Okay, let me say this is for x greater than 0. So now if I have x smaller than 0, so I cannot do ddx log of x because right, as I said, the log function is not defined when x is smaller than 0. But let me consider this. I'm considering ddx log of minus x. Now this is okay because I'm considering x smaller than 0, right? So that means the log of minus x. That means the minus x is actually a positive number. Then this is okay, right? So if I do this, then let me just apply chain rule, right? So it would be 1 over minus x times d dx minus x. And this would be, again, 1 over x. So I have actually two cases. If I want to combine these two cases in one formula, okay, so what I would write down this. Okay, you see what I'm right here is that the log of the absolute value of x is equal to 1 minus x. Okay. So for x greater than 0, so you don't need to think about anything, right? So, but as I said, right, for x smaller than 0, so the derivative of log of minus x is 1 over x, right? So when x is smaller than 0, right? So the absolute value of x by definition is minus x, right? So that's why this is the formula, right? For if you consider both x is positive or negative. So then if I go back to this, then it would be log of absolute value of x plus, this is also indefinite integral, then also plus some constant. Of course, this is a constant, this is a constant, then you can just use one constant to represent both of them. So right, so I hope this one, not sure if you have seen this before, right? So with the absolute value, have you seen this before? The log with the absolute value. Okay, that's good. Well, if you are still not so comfortable with it, just consider the graph, right? So if I draw the graph, okay, I should not. If I consider the graph of the function, right? So if I have this 1 over x, right, on the left-hand side, right? So this would be the log of it. Right, something like that. Right, so if you consider the negative side, right, so this would be it. Right, and if you try to take the derivative of this, you can see that it's always negative, right? So, and this would corresponding to this part. Right? So just see the plot. So then I think you'll feel comfortable with this. Okay, here, just two more simple examples, right? So for the separation of variables, so dy dx equals x plus 1 divided by y. Again, all terms related to y go to the left-hand side, right? So all terms related to the x go to the right-hand side. So then I have this y dy equals x plus 1 dx, right? So, and then integrate both sides. Then we're done. This one also, right? So all terms related to y go to the left-hand side. All terms related to x go to the right-hand side. Integrate. Then you got. Okay. So then that's we have done these two, right? So direct integration, which is the trivial one, and then the separation of variables. This is actually a very useful one, right? The separation of variables you use a lot. And then actually, let me stop for today. Okay, so because I've just finished these two of the types, I'll just start again next time. Okay, so I'll just stop.